Throughout all of human history, the sky has been the first mirror of the unknown. From the times when our ancestors gazed at the heavens and saw there the home of the gods, to the modern era of space telescopes and interplanetary probes, one question has never stopped echoing within us. How far does the universe go? Is there an end to space? Or does it stretch on forever without boundaries, without edges, and without any outside we can imagine? These questions are not mere philosophical curiosities. They reach into the heart of cosmology and our very understanding of the nature of reality. The observable universe is, above all, a limit of our vision. It is not a physical boundary, nor a cosmic wall where space ends, but rather the farthest point that light has managed to reach us since the birth of the cosmos. When we look at the sky, we are not seeing the present. We are seeing the past in layers, as if time itself were a transparent fabric. Every star is a window into an ancient era. Every galaxy is a memory of a younger universe. Space is a machine of memory, and the limit of the visible universe is the point where that memory fades, where the past becomes inaccessible because light simply has not had enough time to reach us. Light, no matter how fast it may be, is finite. It travels at about 300,000 kilometers per second, an impossible speed for any known form of matter. Yet even that number becomes small when compared to the cosmic scale. This is because the universe is not static. While light travels, space itself expands. Imagine trying to reach a drifting ship while the entire ocean stretches between you. For this reason, there are regions of the cosmos whose light will never reach us, not because there is a wall blocking it, but because the space between us grows faster than light can travel. What we call the observable universe is a gigantic sphere centered on every observer. Its radius is approximately 46 billion light-years. This means that, although the universe is about 13,800,000,000 years old since the Big Bang, space itself has expanded so much that the distance between us and the first visible lights is much greater than time multiplied by the speed of light. This difference arises because space is not a fixed stage where events occur. It is part of the spectacle itself. The cosmic fabric stretches, bends, and transforms along with time, making the notion of distance something profoundly relative. Within this observable sphere, we find billions of galaxies, each containing hundreds of billions of stars and possibly trillions of planets. Everything we know, everything we can measure, study, or imagine based on evidence, is contained within this horizon. Beyond it, the unknown extends like a shoreless sea. We can estimate, deduce, create mathematical models, but there is no direct way to observe what lies beyond this bubble of light. The limit of the observable universe, therefore, is not the end of the universe. It is the limit of our access to information. The concept of a border becomes problematic when applied to the cosmos. In everyday life, we think of limits as edges, the end of a road, the shore of an ocean, the outline of an object. But the universe, according to Einstein's general relativity, does not need a border to be finite. Just as the surface of a sphere has no end, three-dimensional space can be finite, but without boundaries. If we were to travel in a straight line for long enough, we could, in theory, return to our starting point without ever encountering a wall. It is a counterintuitive, but profoundly revealing concept. The cosmos may be a curved and self-contained space, with no inside or outside, only an endless continuity of time and matter. This vision challenges our intuitive perception. The human brain was shaped to understand the world on small scales, where beginnings and endings are clear. However, when looking at the universe, we must abandon that scale. What lies beyond the visible universe is not necessarily another region filled with new stars and galaxies. It could simply be more space, or perhaps even another universe, with distinct physical laws. Some cosmologists suggest that we live in a cosmic bubble among countless others, inflated within an infinite sea of primordial energy. If that is true, then our universe is only a fragment of an immeasurable mosaic. To understand the limits of the universe, we must accept that we are inside a system in continuous motion. The Big Bang was not an explosion that hurled matter into a void, but rather an expansion of space itself in all directions. There was no central point from which everything emerged. The universe is not expanding outward, it is expanding within itself. This expansion defines the limit of what we can see, but not necessarily of what exists. The cosmic horizon is the point where the past becomes unreachable, where time and distance blur together, and where physics, as we know it, begins to lose its ability to describe reality. To gaze at the edge of the universe is, ultimately, to gaze at the edge of human understanding. The frontier is not only in space, and it is also within us, because to understand the universe is to attempt to comprehend infinity using a mind born for the finite. It is like trying to measure the ocean with your hands. Yet it is this very attempt that defines us. As the cosmos expands, human curiosity expands as well. The true limit of the universe is the distance between what we know and what we are still capable of imagining. Throughout all of human history, the sky has been the first mirror of the unknown. From the times when our ancestors looked up at the heavens and saw there the dwelling place of the gods, to the modern era of space telescopes and interplanetary probes, one question has never stopped echoing within us. How far does the universe go? Is there an end to space? Or does it extend forever without boundaries, without edges, and without any outside that we can imagine? These questions are not just philosophical curiosities. They touch the very heart of cosmology and our understanding of the nature of reality. The observable universe is, above all, a limit of our vision. It is not a physical boundary, nor a cosmic wall where space ends, but rather the farthest point that light has managed to reach us since the birth of the cosmos. When we look at the sky, we are not seeing the present. We are seeing the past in layers, as if time were a transparent fabric. Each star is a window into an ancient epoch. Each galaxy is a memory of a younger universe. Space is a machine of memory, and the limit of the visible universe is the point where that memory fades, where the past becomes inaccessible because light simply has not had enough time to arrive here. Light, as fast as it may be, is finite. It travels at about 300,000 kilometers per second, a speed impossible for any known form of matter. Yet, before the vast scale of the cosmos, even that number becomes small. This is because the universe is not static. While light travels, space itself expands. Imagine trying to reach a drifting boat while the entire ocean stretches between you. For that reason, there are regions of the cosmos whose light will never reach us, not because there is a wall blocking it, but because the space between us grows faster than the light can travel. What we call the observable universe is a gigantic sphere centered on every observer. Its radius is approximately 46 billion light-years. This means that, although the universe is about 13,800,000,000 years old since the Big Bang, space itself has expanded so much that the distance between us and the first visible lights is far greater than time multiplied by the speed of light. This difference arises because space is not a fixed stage where events occur. It is part of the spectacle itself. The cosmic fabric stretches, curves, and transforms along with time, making the notion of distance something deeply relative. Within this observable sphere, we find billions of galaxies, each with hundreds of billions of stars and possibly trillions of planets. Everything we know, everything we can measure, study, or imagine based on evidence is contained within this horizon. Beyond it, the unknown extends like a shoreless sea. We can estimate, deduce, and create mathematical models, but there is no direct way to observe what exists outside this bubble of light. The limit of the observable universe, therefore, is not the end of the universe. It is the limit of our access to information. The concept of a border becomes problematic when applied to the cosmos. In everyday life, we think of limits as edges, the end of a road, the shore of an ocean, the outline of an object. But the universe, according to Einstein's general relativity, does not need a border to be finite. Just as the surface of a sphere has no end, three-dimensional space can be finite yet without boundaries. If we were to travel in a straight line long enough, we could, in theory, return to our starting point without ever encountering a wall. It is a counterintuitive yet profoundly revealing concept. The cosmos may be a curved and self-contained space, with no inside or outside, only an infinite continuity of time and matter. This view challenges our intuitive perception. The human brain was shaped to understand the world in small dimensions, where beginnings and endings are clear. However, when we look at the universe, we must abandon that scale. What lies beyond the visible universe is not necessarily another region filled with new stars and galaxies. It could simply be more space, or even another universe, governed by distinct physical laws. Some cosmologists suggest that we live in a cosmic bubble among countless others. inflated within an infinite sea of primordial energy. If that is true, then our universe is only a fragment of an immeasurable mosaic. To understand the limits of the universe, we must accept that we are inside a system in continuous motion. The Big Bang was not an explosion that launched matter into the void, but rather an expansion of space itself in every direction. There was no central point from which everything emerged. The universe is not expanding outward, it is expanding within itself. This expansion defines the limit of what we can see, but not necessarily of what exists. The cosmic horizon is the point where the past becomes unreachable, where time and distance blur together, and where physics, as we know it, begins to lose its ability to describe reality. To look toward the limit of the universe is, ultimately, to look toward the limit of human understanding. The boundary is not only in space, it is also within us, because to understand the universe is to try to grasp infinity with a mind born for the finite. It is like trying to measure the ocean with your hands, and yet it is this attempt that defines us. As the cosmos expands, human curiosity expands with it. The true limit of the universe is the distance between what we know and what we are still capable of imagining. Everything we know about the cosmos fits within an imaginary spherical space that we call the observable universe. This sphere, centered at every point in space, represents the maximum limit reached by light since the beginning of time. It is not a physical structure, nor a solid boundary. It is a concept based on the finite speed of light and the age of the universe. Every observer, anywhere in the cosmos, lives within their own observable bubble, defined by the distance light has traveled since the Big Bang. The fascinating part is that this bubble is not the same for everyone. Each hypothetical civilization in another corner of the universe would see a different portion of reality. The observable universe has a radius of about 46 billion light-years. This means that although the universe is approximately 13,800,000,000 years old, the expansion of space makes the most distant objects much farther away than that time multiplied by the speed of light. Space itself stretched as the light traveled, increasing the distances between galaxies. This difference reveals the dynamic nature of the cosmos and shows that space is not a simple arena where events take place, but a living entity that changes with time. To visualize the observable universe, imagine an immense balloon being inflated. The galaxies are not moving through the balloon, but with it. As the balloon expands, the points on its surface move away from one another. The same happens with the universe. There is no center, no edge expanding outward. The entire structure grows uniformly, and every point can be considered the center of the observable universe from the perspective of its observer. This cosmic symmetry is one of the most striking ideas in modern cosmology. The universe appears the same in all directions on large scales. Modern space telescopes are the most powerful windows we have ever opened to this immensity. The Hubble Space Telescope revealed thousands of galaxies in a single patch of sky, showing that the cosmos is more populated than any mind could ever imagine. The James Webb Space Telescope, with its ability to observe in infrared wavelengths, can see even farther, literally deeper in time. It captures the light of galaxies formed when the universe was only a few 100 million years old, revealing the first structures that emerged from primordial chaos. The Planck Observatory, in turn, mapped with precision the cosmic microwave background radiation, providing a portrait of the universe when it was still a cosmic child, less than 1 million years old. These maps are not merely ancient images, they are records of the very texture of space-time, small variations in temperature that reveal the seeds of galaxy formation. Each cold and warm spot in that diffuse background is a clue to how matter gathered to form everything that exists today. It is as if we were looking at the invisible mold of the universe. Within this sphere of 46 billion light-years, what we see is only a tiny fraction of what truly exists. The most recent estimates suggest that the observable universe contains around 2 trillion galaxies, each with hundreds of billions of stars. Even so, that number is a microscopic sample compared to the possible whole. If space is truly infinite, what we observe is merely a single point in a boundless ocean. Most galaxies are so far away that we will never be able to reach them, not even with light. The observable universe is, ultimately, a time capsule, a window into the past. not a photograph of the present. This perspective completely changes our notion of distance. When we say that a galaxy is 10 billion light-years away, we are seeing it as it was 10 billion years ago. What it is now may be entirely different, or it may no longer exist at all. Time and space on a cosmic scale intertwine in such a way that the concept of now loses its universal meaning. Every direction we look is a journey through time, and every photon that reaches our eyes is a memory from a distant era. Astronomers build detailed models of the observable universe by combining direct observations, radiation measurements, calculations of spatial curvature, and computer simulations. These simulations reproduce the growth of cosmic structures, from the earliest fluctuations to the colossal web of galaxies that forms the current universe. The result is a grand vision, a cosmic network with immense filaments connecting clusters of galaxies, interspersed with vast voids nearly devoid of matter. This structure resembles a three-dimensional web, and each node of this web is a galaxy or a group of galaxies. It is the skeleton of the cosmos. However, the observable universe is only a slice of reality. It represents what we are able to see, not necessarily all that exists. The invisible portion may be far larger, perhaps infinite. There are regions so distant that not even the light emitted at the very first instant of the Big Bang could ever reach us, due to the accelerated expansion of space. These places lie beyond our cosmic horizon, beyond any possibility of observation. The boundary between the observable and the unobservable is the point where science touches the edge of mystery. The observable universe, therefore, is a definition of perspective, not of totality. It is the maximum that light can reveal, and within it lie all the enigmas we have managed to decipher. But there is a fundamental difference between what we can see and what exists. Perhaps the universe is finite yet without edges. Perhaps it is infinite, repeating itself like an endless mirror. The truth is that the visible universe is only the beginning of the story. Beyond it begins the territory, where neither light, nor time, nor human understanding can advance. The universe is a movement in itself. It not only contains galaxies, stars, and planets. It is the very expanding stage upon which everything takes place. Since the instant of the Big Bang, space has never stopped growing. It was not an explosion in the usual sense of the word, because there was no central point and no void into which matter was thrown. The Big Bang was the expansion of space itself, and every point in the universe is moving away from every other point. It is this expansion that defines cosmic horizons and places us before the strangest of frontiers, a frontier that is not physical, but geometric. When astronomer Edwin Hubble observed, in the early 20th century, that galaxies were moving away from each other, he revealed the dynamic nature of the cosmos. The universe is not static as once thought. It is growing, and the farther a galaxy is, the faster it recedes. The relationship between distance and velocity, known as Hubble's law, is one of the clearest proofs of universal expansion. This discovery changed everything, for it showed that the universe had a beginning and that it is in constant transformation. The expansion of the universe creates the concept of the cosmic horizon. This horizon is not a physical edge, but a natural limit of observation. It is the maximum distance that light has had time to reach us since the Big Bang. Everything beyond it remains hidden, not because it lies behind something, but because light simply has not yet traveled far enough. The horizon is the point where time and space intertwine, revealing how we remain prisoners of the speed of light. But there is another kind of horizon, more dramatic and absolute, the cosmic event horizon. It marks the final line of possible communication between regions of the universe. There are galaxies so distant that the light they emit today will never reach us, because the space between us and them is expanding faster than light can cross. There is no violation of physics in this. It is not the galaxies moving through space, but space itself growing between them. This horizon is the ultimate limit of our causal reach. Beyond it, events cease to have any connection with our future. This phenomenon creates a melancholy consequence. The visible universe is shrinking in terms of accessibility, even as space itself continues to grow. With every passing billion years, new regions cross the event horizon and vanish from our reach. The most distant galaxies fade into ever fainter points until they disappear completely, swallowed by the growing darkness of accelerated expansion. In the far future, the visible cosmos will shrink to a handful of nearby galaxies bound together by gravity, while the rest of the universe fades beyond our reach. It will be like living on an island of light, surrounded by an infinite sea of darkness. The acceleration of expansion is one of the greatest mysteries of modern cosmology. Discovered at the end of the 20th century, it contradicted the expectation that gravity should slow the growth of the universe over time. Instead, observations revealed that galaxies are moving away faster than before. This acceleration is attributed to an enigmatic entity known as dark energy, a form of energy that permeates all of space and acts as a repulsive force, pushing the cosmos outward from itself. We still do not know what it is, but we know that it represents about 70% of the total content of the universe. Expansion also redefines our understanding of distance. In an expanding universe, measuring space is not simple. A galaxy that today appears to be 30 billion light-years away was much closer when it emitted the light that now reaches us. Space stretched during the light's journey, continuously altering the distance. That is why speaking of the size of the universe requires caution. The value depends on how we define distance itself, whether based on the time light took to reach us or on the current position of the galaxies that emitted it. In any case, all measurements reveal the same truth. The universe is in constant and irreversible motion. The cosmic horizon, therefore, is more than a boundary line. It is a reminder that the universe is not a static scene, but a flow of events receding from us in time and space. What we see is a sequence of echoes, a collection of ancient portraits of a cosmos that has already changed. Each distant galaxy is a memory frozen in light, each photon is a witness to expansion, and each horizon is a frontier that moves forever, retreating from us as time itself advances. To understand the horizons of the universe is to accept the transient nature of observation. What we can see today will one day no longer be visible. The cosmos is not only expanding, it is fading before us, slowly, like a bonfire consuming its own fuel. This expansion does not destroy the universe, but separates it. It creates distances that can never be crossed, and boundaries that even light cannot overcome. Yet within this vastness in retreat, the very fact that we can look and understand part of this process is a testament to our connection with the whole. Because even in the face of infinity, the human being continues to try to measure the impossible. The idea of infinity has always fascinated and terrified the human mind. It exists both in mathematics and in philosophy, but when applied to the universe, it becomes an almost unreachable concept. Is the universe infinite? Or is there a maximum size, a defined extension beyond which space simply ceases to exist? The answer, though still incomplete, leads us to the heart of modern cosmology, the point where science and mystery meet. To understand the notion of an infinite universe, one must first grasp what size means on a cosmic scale. According to Albert Einstein's general relativity, space is not merely a void where objects move. It is an elastic structure, capable of bending under the influence of gravity and energy. This means that the universe does not need to be infinite in order to have no edges. It can be finite yet without physical boundaries, like the surface of a sphere, which is finite in area but has no point where it ends. If the universe is like this, we could travel in a straight line forever and, after enough time, return to our starting point without ever encountering an edge. However, the most precise measurements made to date indicate that the universe is practically flat. This means that, on large scales, the sum of the angles of a cosmic triangle approaches 180 degrees, and parallel lines never meet. This flat geometry is what would be expected of an infinite universe, though it remains possible that it is merely so vast that its curvature is imperceptible to our instruments. In other words, the universe may be finite but appear infinite from our point of view, just as Earth's surface seems flat to those who walk upon it. The cosmic plane was confirmed by measurements of the cosmic microwave background radiation, particularly by the results of the Planck Observatory. These observations showed that the universe is homogeneous and isotropic on large scales. In other words, it appears the same in all directions. This balance suggests that, if the universe is curved, the curvature is extremely small, so small that it lies beyond our current ability to detect. This leads us to the hypothesis that the universe may indeed be infinite in extent, with no endpoint, no boundaries, and no outside into which it expands. But what does an infinite universe mean in physical terms? It means that matter, galaxies, and cosmic clusters repeat themselves endlessly in all directions. Each region of space would contain similar structures, and perhaps even distant replicas of the same galaxies, stars, and planets. In an infinite cosmos, every possible configuration of atoms would occur somewhere, repeated across unimaginable intervals. On inconceivable scales, there would be regions identical to ours, with versions of ourselves living other variations of reality. This is one of the most dizzying implications of infinity. Everything that can exist does exist, not once, but infinitely many times. Modern physics, however, still has no definitive answer. The observable universe is limited by the light we are able to detect, and everything beyond that horizon remains out of reach. We can infer that space continues, but we cannot prove it. Even so, the equations of general relativity allow for solutions describing universes of many kinds: finite, open, closed, and flat. Each of these possibilities represents a different form of cosmic geometry. A closed universe curves back upon itself, like a sphere. An open universe extends infinitely, like a plane. A flat universe is a delicate balance between these two possibilities, and it is precisely this balance that seems to define our cosmos. The idea of infinity also raises a profound question about time. If space is infinite, is time infinite as well? Or could the universe be spatially infinite yet finite in duration? Observations indicate that the universe had a beginning, the Big Bang, and that time as we know it was born there. This implies that the universe may be infinite in space but not in time. It had a point of origin and perhaps will have an end, even if space itself never ceases to exist. It is a fascinating paradox, an infinity that began at some point. The notion of an infinite universe also changes the way we think about the center of the cosmos. If the universe has no boundaries, it has no center either. Every point is equally central, and expansion occurs in all directions at once. There is no privileged place in space. An observer in any galaxy could consider themselves the center of the observable universe, and they would be correct within their own perspective. This cosmic equality is one of the most beautiful ideas in modern physics. The universe has no absolute reference point, and no observer is more central than another. If the infinity of the universe is confirmed, it would also change our perception of cosmic loneliness. Because in a truly infinite universe, we are not isolated, only limited by distance. The same physical laws that shaped our sun and our earth may be at work in billions of other places, creating countless similar worlds, some perhaps even harboring life. Infinity is not emptiness. It is filled with possibilities. Every particle, every atom, and every ray of light is part of an endless tapestry. To think of an infinite universe is to confront the limits of human reason. Infinity is not merely a spatial extension. It is a conceptual challenge. There is no number, measurement, or image that can contain it. It is the purest reflection of what lies beyond comprehension. And paradoxically, it is precisely our inability to grasp it that makes infinity so powerful. It reminds us that human knowledge is but a small flame before the ocean of existence. Yet it is that very flame that lights the way. The universe may be finite yet without edges, or it may be infinite, stretching on forever. In either case, it is greater than anything we can imagine. The question perhaps is not whether the universe has limits, but to understand that the very concept of a limit loses meaning when speaking of the cosmos. In the universe, every answer is a new frontier, and every discovery opens doors to even more distant horizons. The structure of the universe is shaped by something invisible yet essential, the geometry of space itself. The cosmos is not merely a three-dimensional stage where galaxies float. It is a fabric that bends, deforms, and stretches according to the distribution of matter and energy. This idea, introduced by the theory of general relativity, revolutionized our understanding of the universe. Space and time ceased to be separate, rigid entities and became a dynamic, interconnected web. The geometry of the cosmos is, therefore, the invisible map of its destiny. According to Einstein, the presence of mass and energy distorts space-time. This curvature is what we perceive as gravity. The Earth orbits the Sun not because a force pulls it, but because the space around the Sun is curved, and the Earth simply follows the straightest possible path within that curvature, what we call a geodesic. Thus, The entire universe can be seen as an immense flexible surface shaped by concentrations of matter, energy, and radiation. What happens locally in a star or a galaxy influences the global shape of space. On a cosmic scale, this curvature defines three fundamental possibilities for the geometry of the universe. It can be closed, flat, or open. A closed universe is one with positive curvature, like the surface of a sphere. In that case, space would be finite but without borders. We could travel indefinitely in a straight line, and after an unimaginable cosmic journey, return to our starting point. A flat universe, on the other hand, would have zero curvature, similar to an infinite sheet, implying unlimited extension without return. An open universe, with negative curvature, would resemble a saddle, expanding infinitely with geometries diverging in all directions. Determining which of these geometries describes our universe is one of the greatest achievements of modern cosmology. Through observations of the cosmic microwave background radiation and the distribution of galaxies, scientists have discovered that the cosmos is astonishingly flat, with a minimal margin of error. This does not mean that it is perfectly flat. Small variations may exist, but it suggests that its curvature, if any, extends across scales beyond our ability to measure. This flatness is one of the great mysteries. It requires such a precise balance of density and energy that it seems almost impossible to have occurred by chance. The theory of cosmic inflation offers an elegant explanation for this geometry. It proposes that, in the first instance after the Big Bang, the universe underwent an extremely rapid expansion, growing exponentially within fractions of a second. This process would have stretched space in such a way that any original curvature was smoothed out, like a bubble inflating until it appears flat over a small region. This inflation also explains the homogeneity of the cosmos, that is, the fact that the universe appears the same in all directions. Even regions now separated by inconceivable distances would once have been in causal contact before inflation drove them apart. Cosmic geometry also defines the destiny of the universe. In a closed universe, gravity would eventually overcome expansion, causing the cosmos to collapse in on itself in an event known as the Big Crunch. In an open universe, expansion would never end, leading to a cold, diffuse, and silent cosmos. In a flat universe, expansion would continue indefinitely, slowing down but never fully stopping. Current observations point toward this third possibility, with dark energy accelerating the process and driving galaxies farther and farther apart. The most intriguing aspect is that, in a curved universe, the concept of an edge loses meaning. The surface of a sphere is finite, yet it has no end. The same applies to three-dimensional space. It can be finite, but without boundaries. There is no outside of the universe because space is not contained within something larger. It is everything that exists. If the cosmos could be visualized in its entirety, it would resemble a four-dimensional hypersphere, impossible to be fully represented by the human mind. In such a structure, every point is part of a continuous whole, and the very notion of a limit dissolves within geometry itself. To understand this curvature, we can imagine an ant walking on a balloon. To the ant, the surface seems flat because its perception is limited. But as it travels greater distances, it would notice that parallel lines converge and that space curves back onto itself. The universe is the same. It may appear flat and infinite from our point of view, but on immeasurable scales, it may fold back on itself, connecting distant regions in ways we have yet to perceive. The geometry of the cosmos also has profound implications for the passage of time. Where space curves more intensely, time slows down. Near massive objects like black holes, time flows more slowly compared to less dense regions. This means that the very rhythm of the universe varies according to its geometry. Space and time are inseparable, and each continuously influences the other. Ultimately, understanding the geometry of the cosmos is to understand the invisible balance that sustains all existence. The universe may be flat, curved, finite, or infinite, but in every possible form there exists a mathematical harmony that transcends human intuition. The curvature of space is the mold in which time bends, light travels, and existence unfolds. To look at the cosmos is therefore to gaze upon the architecture of infinity itself, a design that can only be seen from within by those who are part of it. There is a limit to what we can see, And it is not the end of the universe. It is merely the reach of light. The cosmic horizon defines the boundary between the visible and the invisible, between the universe we know and the one that will forever remain beyond our grasp. Everything beyond that line cannot be observed, measured, or confirmed, because no signal has yet crossed time and space to reach us. And yet it is almost certain that the cosmos continues beyond that limit, expanding into dimensions that our perception will never reach. The universe beyond the horizon is, therefore, the domain of the unknown, a space where physics and imagination intertwine. When we look at the most distant galaxies, we are seeing the most ancient past that light allows us to witness. Every photon that reaches us is a messenger from a lost era, carrying information about a younger, denser and hotter universe. But there is a point where this journey into the past meets a limit, the moment when the universe became transparent, about 380,000 years after the Big Bang. Before that, radiation was trapped in a sea of particles, and no light could travel freely. Everything that happened before that instant lies beyond light, and thus beyond direct observation. Yet the universe does not end there. What lies beyond the horizon may contain entire regions with structures similar to ours, galaxies, stars, planets, perhaps even forms of life. The expansion of space makes these regions recede from us at speeds greater than that of light, rendering them invisible and unreachable. But that does not mean they cease to exist. They remain there, following their own course within the vast cosmic ocean. What changes is our relationship with them. The space between us grows faster than light can cross, creating an abyss of silence that will never be bridged. This concept is profoundly counterintuitive. When we think of distance, we imagine a path that can be crossed. But on a cosmic scale, there are places to which no journey is possible. Not because they are far, but because the very space between us and them is growing. It is a distance measured not in kilometers, but in impossibility. There are regions of the universe that have existed, exist now and will continue to exist, yet will never share a single piece of information with us. They are worlds beyond our event horizon, sealed off by the eternal expansion of space. Cosmologists believe that the universe may be much larger, perhaps infinitely larger, than the part we can observe. If space is truly flat, as observations suggest, then nothing prevents it from extending endlessly, far beyond our bubble of 46 billion light-years. Within that immensity, what we call the observable universe would be just a tiny region, a speck of dust within an incomparably greater structure. The theory of cosmic inflation reinforces this idea. According to it, in the first instance after the Big Bang, the universe underwent such a rapid expansion that regions once connected were separated forever. This inflation would have created an immense cosmos, composed of areas that could never again interact. The part we observe would be only a small bubble within a vast sea of bubbles, each with its own physical laws, constants, and properties. This concept is known as the inflationary multiverse, a collection of isolated universes, each with its own horizon and its own history. In some of these universes, conditions may resemble ours, allowing for the formation of stars, planets, and life. In others, the fundamental forces may differ. Gravity might be stronger, or time might flow differently. These possibilities, however speculative, reveal how limited our understanding of everything still is. Even if we can never confirm the existence of other universes, the very logic of physics suggests that ours is not the only one possible. The universe beyond the horizon is also a mirror of human limitation. It reminds us that all knowledge is shaped by perspective. Our telescopes, however powerful, are windows open only to a certain depth of the past. What lies beyond them belongs to the realm of silence, a silence that is not absence, but an excess of distance. There is something profoundly poetic in that boundary. It is the realization that the universe is greater than the very possibility of measuring it. Even so, science continues to reach for the invisible through inference and calculation. Gravitational waves, for example, allow us to hear distortions of space-time coming from regions inaccessible to light. These signals open new windows to the unknown, revealing events that occur billions of light-years away, in places where brightness will never arrive. Each detection is proof that the cosmos speaks in many voices, and that the horizon of light is not the end of knowledge, but the beginning of another way of seeing. To think about the universe beyond the horizon is to recognize that we live within a moving frontier. At every instant, space expands and the horizon recedes, carrying away worlds that were once within our reach. The cosmos is retreating, and we, tiny observers, remain in a small refuge of light that shrinks amid the growing darkness. Yet there is beauty in this distancing, because when we gaze toward the limit, we do not only see the end of the visible, we also see the power of human curiosity, which insists on moving forward even when there is no longer light to guide the way. Time is the invisible axis upon which the universe is built. It is not merely the sequence of events, but a real dimension, intertwined with space, shaping and being shaped by everything that exists. To speak of the limits of the universe without speaking of time is like trying to understand the ocean without considering its tides. Time defines the direction of the cosmos, the measure of its expansion, the rhythm of its history, and the boundary of our own perception. In the classical view, time seemed like a continuous uniform line flowing from past to future independently, but general relativity changed that notion forever. Einstein showed that time is not absolute. It bends, stretches, and contracts according to gravity and motion. This means that the time experienced by a star near a black hole does not pass in the same way as time on a distant planet, or the time measured by us here on Earth. Time is malleable, and this malleability is one of the keys to understanding the universe. The Big Bang, the event that marks the birth of the cosmos, was also the birth of time. Before it, there was no before in the physical sense. Time began there, along with space, energy, and matter. To ask what existed before the Big Bang is therefore meaningless within the known laws of physics, because before itself did not exist. The clock of the cosmos began ticking at that instant, about 13,800,000,000 years ago. Everything we know, stars, galaxies, planets, life, is a consequence of the expansion of time and space from that initial point of extreme density. However, time does not flow in the same way throughout the universe. Where gravity is stronger, it slows down. Where it is weaker, it speeds up. This phenomenon is known as time dilation. In regions near black holes, time practically freezes for an outside observer. In the vast intergalactic voids, where there is almost no matter, time flows more freely. Thus, the cosmos is a mosaic of rhythms, where every place has its own temporal cadence. This variation is imperceptible in daily life, but on a cosmic scale it creates profound effects, altering how we interpret the past and the future. There is an inseparable link between time and the expansion of the universe. Space is growing, and time is the record of that expansion. Cosmic time is not measured by human clocks, but by the age of galaxies, the light of ancient stars, and the temperature of the cosmic microwave background. As the universe expands, radiation cools, rhythm slows, and events become more spread out. The cosmos itself ages, and every passing second is a direct consequence of expansion. Time also defines what we can observe. When we look at the sky, we are not seeing the universe as it is, but as it was. The galaxies we observe today existed billions of years ago. Their light has traveled for eons before reaching our telescopes. The time of observation is, therefore, a delayed time. There is no universal present, only overlapping pasts. Every direction we look reveals a different stage of cosmic history, making space a kind of three-dimensional archive of time. What we call the horizon of the universe is, in fact, the temporal limit of light. It is the maximum distance that radiation has had time to travel since the beginning of the cosmos. Beyond that point, there is no absolute darkness. There is a time that has not yet arrived. Those regions are unreachable not only because of distance, but because of age. Time, in its very structure, defines what is possible to know and what will remain forever beyond our reach. The laws of physics, as far as we know, are symmetric in time. They work both forward and backward. Yet the universe has a clear temporal direction, what we call the arrow of time. This arrow points from past to future and is linked to the increase of entropy. That is the natural tendency of the universe to move from ordered to disordered states. The Big Bang represented the point of minimal entropy, and since then the universe has been moving toward maximum disorder. That is why we remember the past but not the future. Time flows in the direction in which entropy grows. The existence of an arrow of time gives the universe a narrative, The birth of stars, the formation of planets, and even life itself are chapters in this cosmic story. Each transformation follows the current of time, dissolving old structures and giving rise to new ones. Time is the invisible sculptor of the cosmos, slow but relentless. And although it seems like a force pushing us toward the end, it is also what allows the existence of everything that changes, evolves, and flourishes. On the other hand, time is also relative to perception. On a human scale, it feels like a constant flow. On a stellar scale, it is almost motionless. The universe shows us that time is not a single river, but a network of currents flowing at different speeds. Every particle in the cosmos has its own time, and all these times coexist within a continuous fabric. When we say that the universe has an age, we are simplifying something infinitely more complex, a collection of times that coexist and intertwine like waves in an ever-moving sea. The role of time, therefore, goes beyond the measurement of moments. It is the very structure of reality. Space without time would be a motionless picture. Time without space would be an empty concept. It is the union of both that creates the universe as we know it, a cosmos in constant transformation, where every moment is unique and unrepeatable. To look at time is to look into the heart of being itself, for time not only measures the universe, it makes it exist. The universe we know was born from an instant of unimaginable expansion, a moment so brief and so intense that it defied all known laws of physics. This phenomenon is called cosmic inflation, the event that shaped the foundations of the cosmos and determined everything that would come to exist. During a minuscule fraction of a second after the Big Bang, the universe expanded exponentially, growing from a subatomic size to astronomical dimensions. It was in that flash of time that space was smoothed, energy was distributed, and the cosmic geometry we know began to take form. Before inflation, the universe was an incredibly dense, hot, and unstable region. On such small scales, gravity and quantum physics intertwined, and the laws we know ceased to make sense. Amid this primordial chaos, an unknown force, possibly linked to an energy field called the inflaton field, triggered accelerated expansion. This expansion was so rapid that, in less than a trillionth of a second, the universe grew more than it would in billions of years of normal expansion. The concentrated energy turned into space, and space began to generate more space, multiplying like a wave that meets no resistance. Cosmic inflation explains a series of mysteries that, before it, seemed unsolvable. One of them is the so-called horizon problem. The universe is astonishingly uniform. The temperature of the cosmic microwave background radiation is nearly the same in every direction, with variations of only 1 part in 100,000. This would be impossible if such distant regions had never been in contact with one another. Inflation solves this by showing that before expanding, those regions were close enough to reach thermal equilibrium. When the universe expanded abruptly, this homogeneity remained, now on colossal scales. Another problem solved by inflation is the flatness problem. Measurements show that the universe is almost perfectly flat, but that flatness is extremely unstable. Any small initial curvature would have grown over time, making the universe very different from what we observe today. Inflation, however, stretched space so violently that any original curvature was leveled out, like a wrinkled sheet becoming smooth when pulled from all sides. The result is the flat cosmos we observe today, where geometry appears balanced on a delicate edge between the finite and the infinite. Inflation also provides an explanation for the origin of cosmic structures. During this phase of expansion, small quantum fluctuations, tiny random variations in energy density, were amplified to astronomical scales. These fluctuations became the seeds of everything that exists: stars, galaxies, clusters, and even ourselves. The universe we see today, with its vast webs of matter and intergalactic voids, is the result of the growth of those initial quantum ripples. In a certain sense, every galaxy is a physical memory of a microscopic fluctuation that occurred in the first instance of existence. The evidence for inflation does not come from direct observation, but from its consequences. The pattern of the cosmic microwave background, the residual glow of the Big Bang, shows variations that match exactly what inflation predicts. Those tiny irregularities, captured by telescopes such as Planck and WMAP, are the fossilized imprint of the first ripples in the fabric of space. Moreover, the spectrum of these fluctuations is almost, but not exactly, uniform, indicating that they were born from quantum processes occurring during inflation. The precision of these coincidences is so great that many physicists regard inflation as one of the most successful theories in modern cosmology. However, cosmic inflation raises an even deeper question. If space can expand exponentially, what prevents it from continuing to expand in some regions? The answer may be nothing. The theory predicts that inflation can be eternal on a global scale. While in some regions it ceases, allowing galaxies and stars to form, in others it continues indefinitely. Each time a bubble of space stops inflating, it gives rise to a local universe, like ours, embedded in an infinite ocean of other universes still expanding. This is the foundation of the inflationary multiverse art idea. If this hypothesis is true, our universe would be just one bubble among countless others, each with its own physical laws, fundamental constants, and cosmic histories. Some could have different dimensions. Others might never allow atoms or life to form. It is a dizzying vision. The cosmos as an infinite field of universes in gestation, being born and drifting apart forever. From that perspective, what we call everything would be only a minuscule fragment of an endless structure. Cosmic inflation redefines how we think about the beginning. The Big Bang ceases to be a singular point, becoming instead a transition. The instant when inflation ended and the universe began to behave normally, allowing matter and radiation to form. The true beginning, therefore, may lie even further back, in a time we cannot measure, in a phase of pure energy where space and time did not yet exist as we know them. The philosophical impact of this idea is profound, because if the universe is just one bubble among an infinity of bubbles, what does that mean for the singularity of our existence? Perhaps we are not the inevitable result of creation, but merely one of the infinite possibilities that space and time allow. And at the same time, perhaps every particle within us is a direct memory of that first breath of inflation, the moment when nothing began multiplying into everything. Since the dawn of modern cosmology, one of humanity's most profound questions has been whether the universe will have an end, or whether it is eternal, repeating itself in infinite cycles of creation and destruction. Time, which began with the Big Bang, appears to follow a linear path, yet there are theories suggesting that the cosmos may be reborn, restart, and replay its history like a cosmic phoenix. The universe we know may not be the first, and perhaps not the last. For a long time it was believed that the fate of the universe depended on its density. If there were enough matter, gravity would eventually slow expansion and reverse it, leading to a final collapse known as the Big Crunch. In this scenario, the cosmos would gradually contract, galaxies would draw closer, stars would collide, and all matter and energy would return to a point of infinite density. It would be the mirror of the Big Bang, an end that prepares for a new beginning. After total collapse, a new expansion could occur, initiating another cycle, a new universe rising from the ashes of the old. As observations advanced, however, an astonishing discovery emerged. The expansion of the universe is not slowing down, it is accelerating. This acceleration, driven by dark energy, seems to push galaxies away from one another at an ever-increasing rate. Instead of a universe contracting under gravity, we see a cosmos stretching faster and faster. This discovery completely changed the perspective on the universe's final fate, opening the door to other scenarios just as grand and just as tragic. One of them is the Big Freeze, also known as heat death. In this future, expansion continues forever, thinning matter and energy until everything becomes cold and inert. Stars would burn through their fuel, planets would freeze, and galaxies would drift so far apart that their light would never reach each other again. Over trillions of years, only black holes would remain, slowly consuming the last traces of energy. Eventually, even these giants would collapse through radiation, leaving behind an empty, silent universe, an eternal night where time still exists, but nothing ever happens again. Another possible scenario is the Big Ripper. In this vision, dark energy not only accelerates expansion, but intensifies it exponentially. The result would be catastrophic. First, galaxies would be torn apart, then stellar systems, planets, and finally, even atoms would be ripped apart by the uncontrollable expansion of space. The universe would disintegrate from within until the very fabric of space-time itself would break. This would be an absolute end, the disappearance of the very structure that sustains existence. But there are also more optimistic visions suggesting that the universe may be reborn. Theories of the acyclic universe propose that the cosmos goes through an infinite sequence of expansions and contractions, each giving rise to a new universe with slightly different properties. In this model, the Big Bang would not be the beginning of everything, but merely a transitional phase between two cosmic cycles. Each universe would leave a subtle inheritance for the next, traces of energy, fundamental structures, and perhaps even information encoded in the very fabric of space itself. A modern variation of this idea is the so-called quantum bounce model. According to it, when the universe reaches extreme densities, the effects of quantum gravity prevent total collapse. Instead of a singular point, there would be a bounce, in which contraction turns once again into expansion. The universe would not die. It would merely change phase. This hypothesis suggests that the Big Bang was, in fact, the echo of a previous collapse, the rebirth of a cosmos that never truly ceased to exist. These theories challenge our understanding of time. In a cyclic universe, time would have neither a beginning nor an end, but would behave like a circle, where each cosmic era gives rise to the next. Each expansion and each collapse would be nothing more than the heartbeat of an eternal universe. It is a profoundly poetic yet scientific vision, one that remains consistent with the laws of thermodynamics and relativity. The concept of cosmic eternity also raises philosophical questions. If the universe is cyclic, does history repeat itself exactly the same way? Have there been other versions of us in previous universes, living the same experiences in endless loops? Or is each cycle completely new, with infinite and unpredictable variations? Science has no answer to that, but the very fact that we can ask such questions reveals the depth of our curiosity before the unknown. Even amid so many hypotheses, there is one consensus. The universe is an evolving system. Whether toward the silence of the Big Freeze, the collapse of the Big Crunch, or the rebirth of a new cycle, the cosmos is not static. It is a cosmic organism in motion, governed by laws that make it be born, grow, and perhaps be reborn. With each expansion, new forms of matter and energy appear, new worlds emerge, and new stories begin. Perhaps the universe never had a true beginning, and perhaps it will never have a definitive end. What we call origin and destiny may simply be illusions born of our need for linearity. The cosmos, in its vastness, may be like an eternal ocean, where each wave is a universe rising and fading, and we are but a fleeting instant within that infinite movement. Behind everything we can see in the universe lies an invisible presence that dominates most of its structure, a substance that does not shine, reflect light, or be detected directly. It emits no radiation, interacts with no electric fields, and escapes every instrument humanity has ever built. And yet, its influence is undeniable. This mysterious entity is called dark matter, and it represents one of the greatest enigmas of modern science. Dark matter was discovered not through direct observation, but through the effect it exerts on what we can see. Astronomers noticed that galaxies were spinning too fast to remain bound only by the gravity of visible matter. Stars, gas, and dust. If that were the only mass that existed, galaxies would simply fly apart. Something invisible, however, was holding them together. It was as if an unseen web sustained the universe, keeping it unified through silent forces. This was the first clue that there is far more in the cosmos than our eyes can reach. Later studies revealed that dark matter makes up about 85% of all existing matter. Everything we know, planets, stars, clouds of gas, even our own bodies, accounts for only a tiny fraction of the universe. The rest lies hidden in this enigmatic form of matter. It is the invisible foundation upon which galaxies form, the skeleton that gives structure to the cosmos. Without it, stars would not cluster, planets would not orbit, and the universe would be nothing more than a scattered mist of isolated particles. But what exactly is dark matter? That is the question we still cannot answer. Several hypotheses attempt to describe its nature. One proposes that it consists of unknown particles called WIMPs, weakly interacting massive particles. Another suggests the existence of axions, extremely light particles that could fill space in colossal quantities. There are also theories pointing to sterile neutrinos, even more elusive versions of the particles we already know. None of these ideas, however, have been proven. To this day, no detector has managed to record a single particle of dark matter directly. Despite that, the evidence for its existence is everywhere. The way galaxies move, the speed at which clusters rotate, the gravitational lenses that bend the light of distant stars, all of these reveal the presence of this hidden force. It acts like an invisible framework, sculpting the universe on unimaginable scales. The light of distant galaxies bends as it passes through regions with high concentrations of dark matter, allowing astronomers to map its contours even without seeing it. These gravitational shadows are the only fingerprints left by something we cannot touch. Dark matter is not just a curiosity, it is essential to cosmic history. Without it, the small fluctuations in matter density after the Big Bang would not have amplified enough to form galaxies. It was the gravity of dark matter that pulled in cosmic gas and dust, condensing them into clouds that, over billions of years, gave rise to stars and planets. In a sense, the entire structure of the visible universe was born from something invisible. What we see today is only the surface of a much deeper reality. Dark matter also reminds us of how limited human knowledge is. Even with the most advanced telescopes and particle accelerators, we still cannot decipher its composition. Every attempt at direct observation results in silence. It is as if we were groping through a dark room, guided only by the sound of echoes. This puts our understanding of the cosmos into perspective. Most of it is made of something we cannot even detect, and dark matter is not alone in this mystery. There is also dark energy, even more dominant and enigmatic. While dark matter holds the universe together, dark energy pushes it outward, accelerating its expansion. Together, they make up more than 95% of everything that exists, leaving only a tiny fraction for ordinary matter. The universe, in its entirety, is practically composed of invisible elements. What we can see is just a thin film of reality floating over the abyss of the unknown. This realization completely changes how we understand the cosmos. Perhaps the universe is more of a shadow than a presence. Perhaps the visible is only the surface of a much more complex structure, a limited manifestation of what truly exists. Dark matter and dark energy are the keys to understanding not only the shape of the universe, but also its fate. They determine how the cosmos expands, how it organizes itself, and even how it might end. The search for dark matter is ultimately a search for the limits of human knowledge. It forces us to accept that the universe is larger than our ability to perceive it, and that there are forces and substances entirely beyond our reach. Yet it is precisely this search that keeps the flame of science alive. Each attempt to find it, each new detector built, each simulation run on supercomputers is a step toward understanding the invisible. The mystery of dark matter is also a mirror. It shows that no matter how far we advance, there will always be frontiers beyond which light cannot reach. Frontiers that can only be crossed through curiosity, imagination, and the will to understand what hides in the shadows of the universe. And perhaps it is within that darkness, not the light, that the true essence of the cosmos lies. The universe is not just vast. It is structured according to an architecture that transcends our intuition. Behind the apparent randomness of galaxies and cosmic voids lies a silent geometric order, a symmetry that permeates space and time, forming what many call the eternal geometry, the fundamental design of the cosmos. This geometry is not limited to the three spatial dimensions we can imagine. It is an invisible mesh that extends across multiple dimensions, sustaining the universe and defining how it expands, curves, and connects. To understand this structure, one must abandon the idea that the universe has a simple shape. It is neither a sphere, a cube, nor a plane. It is an entity of variable geometry, shaped by gravity and energy. On large scales, this geometry takes on complex forms known as topologies. Some theories suggest that the universe may have the shape of a torus, similar to a cosmic donut, where space curves and connects to itself. Others describe it as a hypersphere, a three-dimensional surface existing within a four-dimensional space. These ideas are not mere mathematical abstractions. They attempt to explain why the universe appears homogeneous without a center or edges, while still being finite. Imagine walking in a straight line through the cosmos, crossing galaxies, nebulae, and intergalactic voids. In a universe with closed geometry, after trillions of light years, you could return to your starting point without ever encountering a boundary. This is the essence of eternal geometry. Space can be finite, yet without borders. There is no outside of the universe, because space is not contained within anything. It is the very container of existence. The cosmos does not expand into something. It is space itself that grows. Cosmologists use the laws of general relativity to describe this geometry with precision. Einstein's fundamental equation shows that the curvature of space-time depends directly on the density of energy and matter present. Where there is more mass, space bends. Where there is less, it flattens. This variation creates a dynamic balance. The universe as a whole is a combination of curved and nearly flat regions, a cosmic tapestry made of subtle ripples and infinite expansions. But there is something even deeper within eternal geometry, the possibility of multiple connected spaces. This means the universe could have shortcuts, regions where space bends enough to link distant areas together. These shortcuts are known as Einstein-Rosen bridges or wormholes. They are mathematical solutions derived from relativity that suggest the existence of spatial tunnels connecting different points in the cosmos, perhaps even different universes. Although there is still no evidence that they truly exist, their possibility reinforces the idea that space-time is far more flexible and intricate than we can perceive. Eternal geometry also involves the concept of cosmic symmetry. The laws of physics appear the same in every direction we look and in every place we observe. This uniformity, called isotropy, is one of the great enigmas of the universe. Why does everything seem so balanced on such gigantic scales? Cosmic inflation, discussed earlier, offers an answer. By expanding the universe suddenly, it would have leveled its irregularities, creating a homogeneous and symmetrical structure. This symmetry is not accidental. It is the reflection of the fundamental balance between energy and space. However, on smaller scales, this harmony breaks down. The geometry of the cosmos is speckled with gravitational distortions, ripples of matter and energy that propagate as waves through the fabric of space-time. These gravitational waves are the signature of the motion of the most massive bodies. Black holes, neutron stars, merging galaxies. They travel for billions of years, slightly deforming the space they cross. The detection of these waves is one of the greatest achievements of modern science, because it allows us to listen to the geometry of the universe. Each vibration recorded is a note in the silent sound of the cosmos. The idea of eternal geometry also changes our perception of beginning and end. In a curved and continuous space, there is no fixed point of origin. The Big Bang was not an explosion at a specific place, but the expansion of all space at once. Similarly, if the universe ever ends, it will not happen in one particular spot, but everywhere simultaneously. Space, time, and energy are parts of a single totality, and their geometry is both the stage and the actor in this cosmic drama. This invisible structure is so perfect that it can be described with simple equations, yet so profound that it defies any attempt at visual representation. The universe is a living mathematical construction, a harmony of curvatures, symmetries, and dimensions that coexist in delicate balance. Even apparent chaos, the explosions of supernovae, the collisions of galaxies, the death of stars, obeys this underlying order. It is a geometric chaos, governed by eternal laws. The term eternal geometry summarizes a deep truth. The universe is a form in constant transformation, yet whose laws remain unchanged. Matter is born and dies, light travels and fades, but the fabric of space-time endures. It curves, stretches, and recombines, maintaining balance between what was and what will be. The cosmos is, therefore, a living geometry, an infinite architecture that breathes in rhythm with time. And when we look at the sky, we are not merely seeing stars and galaxies, we are contemplating this geometry. Each luminous point is a vertex of a cosmic equation, a part of a design that spans billions of years. Even without fully understanding it, we feel its harmony, the silent balance that unites all things and makes the universe an eternal work, drawn with the invisible precision of existence itself. The idea that the universe might have an end is a legacy of our limited perception. From childhood, we learn that everything around us has margins, boundaries, and edges. The ocean has a shore, the mountain has a peak, the book has a cover. In our daily experience, the end is a constant. It is therefore natural to imagine the cosmos as something that must also end somewhere. But this notion, so intuitive in the human world, completely loses its meaning when projected on a cosmic scale. The truth is that the universe, in its deepest nature, has no edges. The limit we perceive is merely an illusion. When we speak of the end of the universe, the first image that comes to mind is that of an invisible wall, a point where space ends and nothingness begins. However, space is not a physical object with defined borders. It is a relationship between distances, a continuous structure that extends upon itself. There is no outside, because the universe is not contained within anything. It is the very fabric of existence. Asking what lies beyond the universe is like asking what exists north of the North Pole. The concept of outside simply does not apply. To grasp this idea, imagine an ant walking on the surface of a balloon. To the ant, the balloon seems infinite. The more it walks, the more space stretches before its eyes, never finding an edge. Yet the surface is finite. It has a total extension, but no limits or walls. The universe may be exactly like that. Finite, yet without borders. A space curved upon itself where all directions ultimately lead back to the same point. The expansion of the universe reinforces this vision. When we say that the cosmos is expanding, it does not mean it is growing inside a pre-existing void. Space itself is what expands. The galaxies are not moving through empty space. They are being carried along by the expansion of the fabric of space-time. There is no outside into which the universe expands, because space is created as the expansion occurs. The universe grows, but not toward anything. It grows within itself. This absence of edges also explains why there is no center of the universe. No point is privileged, and every observer in any galaxy would see the others receding equally. This happens because the expansion is homogeneous. It occurs everywhere at once. If there were a center, it could be identified, and that would break the symmetry we observe. But the universe has no fixed center. It is like an inflating balloon where each point on its surface moves away from all others uniformly. The illusion of borders arises from the limitation of our senses. When we look at the horizon, we see an apparent end of the world, but we know it is only the curvature of the Earth. The same happens with the universe. The cosmic horizon is merely the limit of what we can observe, not the limit of what exists. What lies beyond it continues to exist, even if we never see it. Thus, the end we imagine is only the end of our vision, not of reality. Einstein's general relativity reinforces this absence of boundaries. In a curved space, it is impossible to trace an infinite straight line without eventually returning to the starting point. The universe may be closed upon itself and still appear infinite to those within it. Time and space are interwoven in such a way that the very concept of edge dissolves. The cosmos, in this sense, is a self-sufficient structure, complete within itself. This notion defies our intuition, but also evokes a singular beauty. To think of a universe without borders is to think of an existence that does not depend on limits to be understood. Space does not need a contour to exist. It is continuous, fluid, and constantly transforming. Every point is connected to every other through the laws of physics, and every particle, no matter how small, participates in this boundless whole. From a philosophical perspective, the absence of borders carries an even deeper meaning. It suggests that the universe is a totality without an outside, and that everything that exists is part of a single continuous reality. There is no separation between inside and outside, between the universe and the void, between being and nothingness. The universe does not need an outline to be complete. It simply is. This is perhaps one of the most powerful lessons of cosmology, that the infinite can be contained within the finite, and that the whole does not need borders to exist. Even so, the human mind continues to imagine what lies beyond. This curiosity is what drives us. We create theories, build telescopes and probes, send messages into the void, as if trying to touch the edges of the impossible. But the universe, silently, teaches us that there are no margins to reach. only new ways to understand the vastness we inhabit. The true frontier is not in space, but in imagination. In the end, the illusion of borders reflects our own need for limits. We are finite beings trying to comprehend the infinite. We seek boundaries because we live within them, but the cosmos invites us to think beyond. It shows us that space is an eternal continuum, with no defined beginning or end, and that every point, every star, and every particle belong to a totality that cannot be contained. The edge of the universe is, therefore, a mirage, and it is precisely this mirage that keeps us exploring. Among the most provocative ideas to emerge from theoretical physics and modern philosophy, none is as unsettling as the hypothesis that the universe might be a simulation, a self-consistent mathematical construction created by intelligences, natural or artificial, existing on some higher level of reality. This possibility, blending science, logic, and speculation, is not merely a philosophical curiosity. It is a direct consequence of the way we understand the laws of nature, precise, regular, universal, and, as far as we know, written in the language of mathematics. If the universe behaves like an information system, it would not be absurd to imagine that it is, in essence, a computation being executed. The simulation hypothesis gained strength from a simple line of reasoning. If a civilization ever reaches a level of technological advancement capable of creating perfect simulations of reality, entire worlds, complete with consciousness, time, and physical laws, then it is likely that such simulations would be numerous, perhaps countless. If each of them were inhabited by conscious beings, the chances of us living in one of these simulated realities would be far greater than the chances of being in the original one. In other words, if the creation of simulated universes is possible, then statistically it is almost certain that we already live in one. But what does it mean to live in a simulation? Modern physics, intriguingly, offers clues that make this idea more plausible than we might wish. The universe is quantized, that is, all of reality is composed of minimal units of energy, time, and space. There is a limit to how small something can be measured, and beyond that point, the notion of continuity disappears. This is similar to a digital system in which reality would be constructed pixel by pixel, bit by bit, with a fundamental resolution. The Planck constant, the minimum limit of quantum physics, would be the cosmic equivalent of the pixel size of the universe. Other clues appear in the way the universe behaves. The laws of physics are universal and immutable, applicable everywhere, like instructions of a code. The fundamental constants, the electron's charge, the speed of light, the strength of gravity, are fixed values sustaining all existence, like parameters of a perfectly tuned program. And elementary particles, rather than being tiny spheres of matter, behave as excitations of energy fields, vibrations in an invisible web of information. The cosmos may therefore be a system of data under continuous computation. Some researchers suggest that the universe might bear signatures of discretization, subtle imperfections revealing its digital nature. For example, if space-time is truly composed of minimal units, then high-energy particles should experience small distortions while traveling long distances, as though crossing a microscopic grid. Detecting such irregularities would, in theory, provide a way to test whether the universe is continuous or computed. To this day, no experiment has confirmed these distortions, but the search continues. Others see the simulation not as a limitation, but as an elegant explanation for the mysteries of physics. Phenomena such as quantum entanglement, where two particles appear to communicate instantaneously, could be manifestations of shared processing, where information does not travel through space, but is updated simultaneously, as in digital systems. Likewise, the impossibility of exceeding the speed of light could be a processing constraint, a kind of maximum refresh rate of reality. The simulation hypothesis also touches the field of consciousness. If the universe is an information system, the mind could be a form of internal processing within that system. Our perception, memory, and emotion would be patterns of information that emerge and interact inside the simulation. This view brings physics closer to metaphysics. Perhaps consciousness is not a product of the universe, but the medium through which the universe perceives itself. From a philosophical standpoint, the idea of simulation is not new. Plato already imagined humanity trapped in a cave of shadows, mistaking appearances for reality. Centuries later, thinkers like René Descartes questioned whether the world we perceive might be an illusion. What changes in the modern era is that these doubts now have a scientific basis. We have equations, computers, and theories capable of turning metaphor into a testable hypothesis. The universe as a simulation is no longer just an allegory. It is a possibility that can be explored. However, even if we were in a simulation, it would not diminish the value of our existence, because within this reality, everything we feel, think, and do is real on its own level. Just as a character in a dream lives their experience fully, we too live ours. And whether the universe is or is not a code does not change the depth of emotion, discovery, and consciousness. Reality in the end may be defined not by origin, but by experience. Furthermore, there is a spiritual dimension to this hypothesis. If the universe is a simulation, there must be a programmer, a higher, conscious, and creative intelligence. For some, this comes close to the idea of God. For others, it is merely a technological metaphor for the origin of existence. But regardless of the name given, the idea that the cosmos was designed by an intelligent mind rekindles the ancient question, why does something exist rather than nothing? The simulation hypothesis does not destroy the mystery, it expands it. Even if we were to prove one day that we live in a simulated reality, the question would remain about the real universe that contains it. And what if that one too were a simulation? The paradox repeats infinitely, forming a chain of realities within realities, like mirrors reflecting one another endlessly. Perhaps the ultimate nature of being is not a physical structure, but a sequence of informational layers that never end. In the end, thinking of the universe as a simulation is, in a way, a modern form of contemplating the infinite. It reminds us that everything we see, from galaxies to subatomic particles, may be just a reflection of something greater, a code that generates beauty, order, and consciousness. And if that is so, then to live is to participate in that code, to feel, think, and exist within the mystery that programs us. Perhaps the true purpose of the simulation is not to deceive, but to awaken. Infinity is perhaps the most powerful and most incomprehensible idea ever conceived by the human mind. It is not merely an endless quantity, it is the absence of limit in every direction of thought. In the context of the universe, infinity ceases to be a mathematical abstraction and becomes a physical possibility, a fundamental feature of reality itself. To ask whether the universe is infinite is also to ask whether existence has a boundary, whether time can end, whether there is a point where being ceases and nothing begins. It is a question that challenges not only science, but the very nature of thought itself. Infinity is not a number, but a condition. In mathematics, it represents that which grows endlessly, that which can never be reached. In cosmology, it takes on an even deeper meaning, that of a universe without borders, stretching forever and perhaps without repetition. It is difficult to conceive of something without limits, because our minds are shaped to operate with beginnings and ends. We live in finite bodies, in worlds with edges, in times that pass. Everything we know follows a cycle, but the universe in its entirety may not obey this logic. It may simply exist, needing neither an initial point nor a final destination. Infinity is present at every level of existence. On microscopic scales, space seems to divide endlessly. Each particle may contain smaller components, and every distance can be subdivided into smaller parts still. On cosmic scales, galaxies drift apart, and there is no sign that this expansion will ever stop. Light travels for billions of years and still fails to reach the whole. It is as if the universe were a mirror reflecting itself in endless layers, each revealing only a fraction of the real. From a physical perspective, infinity is a matter of viewpoint. The universe may truly be infinite in extent, or it may simply be so vast that its curvature is imperceptible, so large that to us it seems without limit. But there is another kind of infinity, more subtle, the infinity of time. Even if space is finite, time may continue indefinitely. The universe may expand forever, cooling, thinning, until it becomes a silent ocean of isolated particles, existing in a time without events. In this sense, infinity is not merely distance, it is duration, it is persistence. The concept of infinity is also tied to the mystery of consciousness. When we gaze at the universe and try to grasp its vastness, something within us expands as well. The human mind, though limited, is capable of conceiving the unlimited. This is the most beautiful paradox of existence, a finite being capable of imagining the infinite. Perhaps that is what connects us to the cosmos, the ability to think beyond the boundaries of time and space, to project thought toward places where the body will never reach. In philosophy, infinity represents the essence of the divine. It is that which cannot be contained, that which cannot be fully explained, that which exists by itself. For the ancients, infinity was the domain of the gods. For modern science, it is the domain of total reality. Yet in both cases it carries the same trait. It is the horizon that can never be reached. Infinity is not something that can be comprehended, only intuited. It exists in every line of light, crossing space, in every galaxy fading into the cosmic horizon, in every instant that passes never to repeat. There is a kind of beauty in the inability to understand infinity, because it reminds us that existence is greater than any explanation. Even the most powerful equations, the most advanced theories, and the most precise telescopes reach only a fraction of the whole. Infinity is what remains when knowledge ends. It is the silence beyond the final question, the space where mystery continues to exist. When astronomers look at the sky and observe galaxies billions of light years away, they are not only studying the past of the universe, they are contemplating the reflection of infinity. Because the farther we look, the more the universe expands. Every new discovery widens the horizon, and every answer opens new questions. Infinity is the very engine of science, the void that drives us forward. And perhaps the deepest meaning of infinity lies in the realization that it exists both outside and within us. The universe stretches endlessly outward, but within the human mind, there is another universe, equally vast, where ideas, emotions, and memories multiply without limit. Each thought is a fragment of the cosmos. Each consciousness is a small mirror of infinity. Thus, infinity ceases to be merely a property of the universe and becomes a condition of existence itself. To think of infinity is to accept mystery. It is to recognize that not everything needs a border to be real, that not everything needs a beginning to exist. The universe does not need an end, just as the sea does not need shores to be immense. Infinity is the natural state of reality, and perhaps also of the soul that contemplates it. In the end, understanding infinity is not a matter of mathematics, but of perception. It is realizing that the cosmos cannot fit into any equation, because the cosmos itself is the living equation of the limitless. The existential meaning of cosmic silence, the human condition between the finite and the infinite, the Fermi paradox as a mirror of our own fragility, an invitation to introspection and interaction. The universe in all its vastness remains silent. No sound crosses the vacuum, no voice echoes between the galaxies. And yet, that silence speaks. It speaks of the distance that separates us from the whole, and at the same time of the invisible bond that connects us to everything that exists. In the midst of infinite expansion, we are fragments of consciousness trying to understand the fabric of which we are part. Cosmic silence is the sound of mystery itself, a presence so profound that it manifests through absence. There is something deeply human in this desire to understand the infinite. In a universe where distances are measured in billions of light years, where light takes ages to cross space, still, a mind within a fleeting body looks to the sky and asks, how far does it all go? This question is more than scientific curiosity. It is the reflection of our search for meaning. Because to understand the universe is in some way to try to understand ourselves. The Fermi paradox reinforces this unease. If the universe is so vast and so ancient, why are we alone? Where is everyone? The absence of signals, the absence of voices, the silence of the stars. All of it feels like an answer we cannot decipher. Perhaps the cosmos is filled with life, but separated by distances even light cannot cross. Or perhaps life is a cosmic rarity, an isolated event amid infinity. Whatever the answer, the paradox reveals something essential. The universe may be immense, but consciousness is still a rare and precious phenomenon. Human beings live between the finite and the infinite. We are made of atoms born in the hearts of stars, yet we live in bodies that age, feel, and die. Each of us carries within the matter of the cosmos and the time of a single instant. This duality is what makes our existence so unique. We are the universe observing itself, aware of its own immensity and fragility. The infinite looks at itself through our eyes. Perhaps the true limit of the universe lies not in space or time, but in the mind that tries to grasp it. Because with each discovery, the horizon moves further away. Science does not close questions, it multiplies them. Knowledge is a form of expansion. When we look at the sky, we are not merely observing stars. We are expanding the boundaries of human understanding itself. In the end, the universe does not need edges, because it completes itself in every particle, in every beam of light, in every thought that tries to reach it. The infinite is not a place, and it is a condition, and we live within it, as brief sparks of consciousness in an ocean that never stops growing. So if tonight the sky feels distant and the silence seems absolute, remember that very silence is the echo of what we are, a fleeting combination of matter, energy, and time, capable of dreaming of the infinite. And before you fall asleep, let this reflection accompany you. Perhaps the universe does not need to answer anything, because the very question, how far does it go, is already proof that we are part of it. Now I invite you to comment where you are listening from, to like this video, and to subscribe to this channel. That way you help expand this journey through the cosmos, exploring each night a new mystery of the universe, as far as light, time, and thought can reach. Sleep well, and see you in the next video.